In this video, I'm going to be talking about gravitational fields, how to draw them, how to calculate them, what they mean. Like normal, I'll give a little bit of theory first, and then I'll give some work examples. Please take a moment to read the success criteria I plan to cover in this video. So let's start off with what actually is a gravitational field. Well, we know from Newton's universal law of gravitation that there's a force of attraction between any two objects with a mass. So we say around any one singular mass, there's going to be a region where we can actually experience that force of attraction. Now notice I've said the word region, and that's because we're talking in 3 dimensions, not 2 dimensions. So it's not correct to say it's the area, but it needs to say region. And that means anywhere around that object, if I put something else, it will experience that gravitational force of attraction. And typically, we don't talk about the force of attraction between you and the person beside you, even though there might be a force of attraction. We usually talk mostly about things like stars and planets, things with a much larger mass. So how could I draw this? Now, my diagram is only in 2 dimensions, but you can imagine I could do this in the 3rd as well. Now, I'm going to take a point mass, and that means a little wee mass that's so small it doesn't have its own gravitational field, or it's so small I can ignore it. It's negligible. And if I put that little wee test mass right here, it's going to be attracted to the center of this much larger mass. And I could put that in multiple places all around, and I'm still going to get that the forces are going to be always directed towards the center. So in this case, to represent that field, I've just imagined top, bottom, left, right, and in between, where should my forces be directed towards the center. And so we can see that quite clearly on our diagram. So now that we know that there's a region where we're going to experience this force, we also need to be able to calculate it. Now we've got this equation here. This is the universal law of gravitation that I was talking about earlier. And in our data booklet, we have what big G is. M1 and M2 will be the masses of the 2 different objects, and some places use a big M and a little m, typically referring to like a planet and a moon around it, but it could be any 2 objects. And don't worry if it has different letters there. And R is going to be the distance between them. I know it says R and you might be thinking, why is it a radius? It's because a lot of the times we are using this with planets. And so they do rotate around one around the other, which is why they get to radius. But it is just the distance between the centers of each mass. So now you might be saying, wait a second, we've been using this little g, and sometimes we've been calling it the acceleration of free fall, but it looks like this. And we've used it to calculate a weight, which is just the force due to gravity. So how does that relate to the universal law of gravitation? Now if you take a look, I've got one mass and this value. Here, this is still force due to gravity. And if I go like this, for example, notice I now have one mass times another value. Well, if we go and we calculate that, gm over r squared, and I use these values from the Earth, 6.67 times 10 to the minus 11. Notice the units here, newtons, meters, kilograms. And I'm going to multiply that by the mass, kilograms, good. Bottom, kilometers. This is a common mistake that people make. It needs to be in meters. So this should be 6.4 times 10 to the power 3, and I have to multiply that by another times 10 to the power 3 to make kilometers into meters. Another common mistake, don't forget to square. Now, I'm going to pick up my handy dandy calculator, and I get 9.77. Now you might think, what are these units going to be? Well, let's work them out. This one had units of newtons, meters squared, kilograms -2 times kilograms. And on the bottom, that would have been meters squared. So let's check this out. This has newtons per kilogram. Only one of them canceled out here. Let me just point out newtons. If I think about Newton's second law of force is mass times acceleration, so hidden inside this newton is going to be kilogram, meter per second squared, now times this kg to the -1, gives me meters per second squared. So that means g, which we were calling acceleration of free fall, is also the same as this gravitational field strength. I can either put here newtons per kilogram or meters per second squared. So I'm going to write up here, what is that little g? It is the acceleration due to gravity or gravitational field strength. One other thing I'm going to point out is we also do have these equations in our data booklet. Notice that's actually what I've just used. G is going to be F over m, or, as I circled here, big G mass divided by radius squared. This value we usually use as 9.8. But to be honest, that value isn't actually always just 9.8. If I go up to a mountain, that's going to decrease. If I'm at the poles, it'll be different from the equator because the Earth isn't a sphere. It's more like a tangerine. It's fatter in the middle than it is up and down. And the density of the Earth underneath it can also change because it's not a homogeneous matter. In some places it's more dense than others. Okay, so let's do an example. We have a mass of 10 kilograms and a weight of 16 newtons. Now remember, weight, that is the force due to gravity, and it's not the same as mass. This is one of the examples where everyday English is not the same as science. Mass is measured in kilograms, weight is measured in newtons, and I'm looking for the gravitational field strength. And from the last slide I was just showing you, that means G. So I'm going to do the force due to gravity, weight, over its mass. 16 newtons over 10, 1.6 newtons per kilogram. Or I could have meters per second squared here. In either way, don't forget to check the units to make sure you're keeping straight whether you have a mass or a weight. A receiver at sea level detects a signal from a satellite in a circular orbit when it's overhead. And it says it's a microwave signal with 68, now notice I've got this underlined, ms. That's not meters times second. That would be impossible. We don't have anything that would be measured in m times s, especially if it's talking about it's received after. This is a time. That is milliseconds. After it's transmitted. Now these are microwaves. Remember, microwaves are EM waves. Why is that important? Well, we know that the speed is going to be 3 times 10 to the power 8 meters per second. So when I want to find the speed, it's going to be traveling at a constant speed. If I'm looking for the height, it'll be just distance is velocity times time. 68 milli is times 10 to the -3. And if I pick up my handy dandy calculator, I get 2.04 times 10 to the power 7 meters. And yes, I'm keeping an extra decimal place here just because I'm going to use it later. Show that the gravitational field strength, okay, so that's again little g, at the position of the satellite is this value. Okay, so let's get our equation, gm over r squared. So from the data booklet, 6.67 times 10 to the -11. I'll need the mass of the Earth. Remember, not the mass of the satellite, the mass of the Earth. And I need the radius. Now the radius is going to have to be from the center of the satellite to the center of the Earth. So in this case, my radius is going to be 6,400 kilometers. Oh, turn that to meters. And then the distance to the satellite. A common mistake is just to use the distance from the surface of the Earth to the satellite. 10 to the power 7. Again, don't forget the square. And if I pick up my handy dandy calculator, I get 0.557. That would be in newtons per kilogram or meters per second squared. And don't forget, because this is a show that question, you must show at least one decimal place more than what they gave you, or the unrounded answer. And as well, show them where you have your values substituted. Depending on the exam, depending on the time, you might not get full marks if you don't put those 2 steps in. And this is approximately 0.56 as required. Okay, example 3. So we've got Saturn here, we've got some information about that. And the first thing says, draw the lines on the diagram to show the shape and direction of the gravitational field. So with my really bad diagram here, I want to touch this up and say a few things about the diagram. So first of all, make them about the same. It doesn't have to be this case. One thing that it does have to do though, is it should be just touching my surface here. It shouldn't go too far. And if I clean that up, oh, you see now I'm not touching there anymore. I need to go back. And these lines need to end on the surface, please. They should be evenly spread because we don't have one side going to be a greater gravitational force than the other, not with a single object, that is a sphere. Next, I'm not going to get full marks because I don't have arrows. And I should be pointing inwards because this is going to be an attractive force. Remember, I could put my little test mass anywhere around here and it should be attracted to the center of this mass. The other thing that's always going to be true about these gravitational field lines, or actually any field lines in general, is they should never cross. If you think about it, if you were putting your test mass here and the lines were crossing, which direction is the force actually being applied to your test mass? That works for gravitational fields, magnetic fields, and electric fields. Part B. It says it's uniform close to the planet's surface. Describe the pattern of the gravitational field lines. Well, if I took this and I blew it up and I was looking closer and closer together, if it's uniform across this place, these gravitational field lines are actually going to look almost parallel. This implies that the gravitational field is going to be constant. One other thing are these lines are going to be perpendicular to the surface. Now, that should make sense to you. You have probably been using 9.8 meters per second squared for all of your work at the surface of the Earth. And you didn't have a different value if you were at the equator or at the North Pole or anywhere in between. That means we had a fairly constant value. But at the same time, now that we were starting to draw these, and since we have Newton's universal law of gravitation, we know that that force of attraction is going to change if I move farther and farther away from the Earth. And now for part C. We've got this moon Rhea and its orbital radius 5.3 times 10 to the power 8 and its mass, and we're asked to calculate the gravitational force keeping it in orbit. Notice that in this case the centripetal force is actually going to be equal to the gravitational force. In some cases they might have given us the speed it's traveling or asking us to find its speed. But in this case we don't have to use that. We're just going to use our universal law of gravitation. Again, I could use m1, m2. If I put in my values, I'm running out of room here. This should still be on the top. The other mass is 2.3. And then all on the bottom, I need to have the radius squared. Now let's double check to see what we were given here. This is the orbital radius. this is not the radius above the surface, so I actually don't need the radius of Saturn in this case, I just need the orbital radius. That does bring up a really good point. And that is that sometimes if we have a radius between two planets that's very large, for example, the distance between the Sun and the Earth, we don't need to worry about the radius of the Sun or the radius of the Earth. And that's because the distance between the Earth and the Sun is so large that we can treat them as point masses. In this case, they've actually given us the orbital radius, the distance from center to center. Now, if I pick up my calculator, I get 3.1 times 10 to the power 20 newtons. Well, I hope that's helped you out. Please take a moment and read the success criteria one more time. I'm hoping that after these examples, you can say yes to all of the points.